Our work for this project is to come up with a prototype of SAFE, architected by Dr. David Mayhew, CTO of Universant Processors. Computer security has become increasingly important with various vulnerabilities and exploits found on a periodic basis in kernel and application software based on attacks such as buffer and heap overflow attacks, side channel attacks, privilege escalation attacks, and even packet sniffing attacks on network systems. As of 2018, computer insecurity was estimated to cost the US economy $250 billion a year. In light of that, SAFE, or Secure Architectural Framework Enhancements, employs a small change in computational architecture to effect a significant difference in its overall security model, while still being compatible with legacy binaries. Its primary goal is to significantly change the operational security mechanisms for computing in general, while preserving application software, minimizing operational costs, and maximizing performance. The primary security mechanism is the use of hardware-managed address spaces, which replace software segmentation found in microkernels like Minix and so forth. It relies on cache-based indices and tags to select from a plethora of accessible address spaces. Fundamentally, SAFE is a hardware-based containerization technology that replaces the lowest levels of a traditional operating system with hardware-based system components. It preserves existing computer architecture models, but modifies the memory model right from the L1 cache up to the last level store, or what can be perceived as a hard disk drive. It completely replaces the microkernel found in modern operating systems with cache-based hardware containerization technology. It also preserves application software by translating the system calls that normally invoke a software kernel in modern operating systems with a safe adaptation layer that replaces them with safe compliant signals. This preserves legacy software and processor architectures and enforces maximal computer security. At this moment of our implementation, we are focusing on the essential components to successfully simulate a safe system, those being the cache hierarchy, the processing node, the process management unit, the secure networking engine, and the last level store, or LLS. The cache hierarchy is a 5-layered cache interface that efficiently migrates cache lines up and down the hierarchy as needed, each layer being 1/4 of the size of the next lower one. For example, an L3 cache line is 1024 bytes in size, so the higher level L2 cache line is 256 bytes in size. This structure drastically reduces the amount of cache tag overhead when compared to legacy systems due to the lack of page tables, and instead just by using context address space tags to label cache lines. Next, the last level store is a crucial component to the functioning and the security of the system. It acts as an intermediary for accessing data for programs and system processes such that all memory references outside the LLS mean nothing by themselves and need to be translated inside the LLS to access the storage. Furthermore, the LLS anchors the cache hierarchy by acting as a level 6 cache and is also responsible for the lowest levels of data object authentication by the use of object authentication tuples. The process management unit manages all of the system's process execution and management. It is a central hub of the system as it handles all the scheduling decisions and is frequently communicating with other components through message notifications. Finally, the secure networking engine replaces the traditional networking software stack with a hardware-based one. It manages all network communications and assigns sockets to their respective network address space tags, or NSASs. We are still in the early stages of implementation and prototyping and are working on simulating a complete system purely on software. But future goals are to simulate all components on a Raspberry Pi to ensure the communication between the system components work as desired, and then analyze which components are used the most to begin an FPGA-based hardware implementation. If you're interested in this project, please watch our complete project presentation later. Thank you so much for listening to our poster presentation, and we sincerely thank our advisors, Dr. David Mayhew, Dr. Mark Johnson, Mr. John Martina, Chris Chiminski, and Cole Nelson. Thank you so much.